One of the bits of kits I rescued from work probably about 3 or 4 years ago was this Ballantine model 9125B Time and Amplitude test set. These were used mainly for calibrating oscilloscopes. We used to make oscilloscopes back in the 60s and 70s, and this would have been used for calibrating the time base and the amplifiers. It'd been kicking around work ever since I started in '94. I remember it being in the storeroom, and people I asked about it, what it was, when I was still learning my ropes, learning the ropes of the company and things. And he said, "Oh, they used it back in the 60s and 70s, probably in the 70s more, and it hasn't been used anymore. No one knew if it worked or not, and it stayed in the calibration room for, well, up until 2015, I think it was. At that point, they had a big clear out where we threw quite a lot of old equipment out that wasn't being used. And as you know, I got a couple of HP signal generators, a spectrum analyzer, and various bits and pieces that were either faulty or redundant. And this was one of the bits I rescued. This unit was actually out for scrap and was about to be picked up by the recycling people, who I think they basically take it away and resell it, or they break it down for scrap. I'm not sure what they did, but anyway, I saw this and I thought, I can't let that go. I say that for most things, but particularly this piece of kit, I thought that could still be useful. Anyway, I sat in the workshop for a year, I suppose, and then I decided I'd just have a fiddle about with it. It seemed to work, loosely speaking, it seemed to work fairly well. But it came into its own when I did a couple of repairs on, I don't know if anyone remembers my 2235, I think it's 2235 analog Tektronix scope, about 3 years ago, when I replaced the cathode ray tube. It had a damaged cathode ray tube, and I used it for that, and it was great because it's all these time bases basically represent the time base you'd expect to see on a scope anyway. And likewise, the amplitude, basically that's your volts per division, and that's your time base. So it was great for that. And that's probably the last time I've used it properly for anything. But I thought I'd dig it out this evening just to see if it still works, and just to show you through exactly what it does. And hopefully, if I can remember how it works, I'll show you. So this is obviously the power switch on. I'm going to meter in the middle. Most of the time that meter's not doing anything, and you don't use that. All it is, it shows you its percentage deviation from the standard. And the unit is basically split between the meter here, with volts here and a DC level or an AC level here, and a marker space marker generator, I suppose, and a time generator this side. It's crystal controlled. I think it is oven crystal controlled, but it's not super accurate. But therefore, it doesn't really need to be for as an oscilloscope. 0.5%, 1% would probably be absolutely fine for time-based references and things like that. We've got an output on the left here, you see, and this is a fixed line frequency. So this is basically whatever's coming in the mains is filtered and given a nice clean signal on this BNC output here. That's that's a 50 hertz reference, good for checking line time bases and things like that. If you want to use a 50 hertz trigger, you could use that. You've got our output mode switch here, and basically what this does is whatever range you've selected, it will. So if I set this range switch here, for example, let's set that to 0.1 of a volt, and that's on DC. That will give me 0.1 of a volt DC. In ground, it obviously is no output, and minus, it's obviously minus 0.1 of a volt DC. And then we've got a square wave generator. So we've got 10 kilohertz here, and that will give us a 10 kilohertz peak to peak of 100 millivolts. 1 kilohertz, 150 kilohertz. No, sorry, 100 hertz and 10 hertz. So basically, we've got a square wave generator for various different amplitudes, and on the right here, as you can see, we've got a multiplied output as well. So if you want 1 volt, you just go times 10, and that will give you a 1 volt output. So you've got a wide range of adjustment for DC levels, and these levels are actually very accurate. I think there's one range that's possibly a little bit out, and I'll have a look, see if I can spot that in a minute on the scope. So that all that output comes out of there, and it's obviously it's capable of quite a lot of volts, because it maximally goes up to what's that? Is that 20? So 20 times 10, so that's 200 volts DC output. So it's capable of sort of at least 200 volts output, and with the deviation wound in even higher than that. So the deviation control is pretty straightforward. If you don't want deviation, you keep the deviation switch off, and if you want the deviation, you've got this pot in the middle, which is basically uncaled, and you see this deviation lights on, so it's in the uncalibrated mode. So you can add a percentage to what you've dialed in here, which is nice. And on the right hand side, we've got a couple of reference outputs, 5 nanoseconds and 2 nanoseconds. They're not particularly clean outputs. They're sort of like, well, I'll show those on the scope later on, but they're good for just checking references and things like that, and they're pretty damn accurate actually. Once the unit's warmed up, it takes a little while for it to warm up. And then we've got basically the same thing as we got on the other side, but obviously markers. I think most of it's square wave or pulse waves. We'll have a look, pulse generator. And the marker outputs come here, and we've got the same sort of multiplication factors as we've got on the DC voltage range. So if we want 0.1 milliseconds and we times it by 10, that's 1 second, you know, so it's pretty straightforward. And then we've got trigger periods here, and these are basically just a time basis, just sent straight out of a clock generator. So we've got 1 millisecond, 10 millisecond, 100 millisecond, 1.5 second, or 1 second, and then all the way around to 100 nanoseconds, and this is on this trigger output here, and this is the output amplitude adjustment here. So it's quite a useful bit of kit for suddenly getting bits of gear going, like checking function generators, counters and frequency counters, things like that. Useful for checking to make sure that everything's sort of in working order. So I think the first thing I'll do is I'll connect it up to the scope, and we'll have a look to see what the outputs are like. And we also like to connect it up, I think, to a DVM, which I think I'll do maybe at a later stage. But let's have a look at the scope output first. We'll look at the right hand side and see what we've got there. But these overhead lights obviously makes this go a bit better. So we'll connect this up now to my HP. We'll connect the marker output connection there, and you can see there we've got some pulse wave. What I'll do is I'll turn off the graticules so they're not so interfering. Where's my display? Okay, clear the cursors. Okay, then we'll just pull up our frequency measuring time, and we'll go period. Okay, so we've got 50, according to the scope, 50 millisecond time-based pulses there, as you can see on the scope. You can see that okay. Just up a bit. That's it. So let's try that. That's working. That's correct. We're on time. Let's go to times 1, and we should be 5 milliseconds. And then you see there. Down so it doesn't flare on the screen. I know the scope tends to flare a bit on the screen, and that's 5 milliseconds there. That's not a problem. So let's try it on some other ranges. Let's try 50 microseconds, and you can see once it's measured at 50 microseconds exactly. So that's good. So this, you can see that clearly works nicely. It gives quite a nice square waveform. Bear in mind I'm not properly terminated. I think there's a 50 ohm termination here. I'm just running straight into the scope's high impedance input. So at higher frequencies you might find that the waveform becomes a little bit crappy, you know, because I'm not matching the output correctly. And you can see here, you see here now you've got more of a sort of like a sort of like a, what would you call that? It's almost like a, I don't know what you'd call that. It's not. It's like almost like a sine wave gone wrong sort of thing. But you can still see we've got clearly a decent 100 nanoseconds, and that's, yeah, one microsecond, 100 nanoseconds, works really well, and very useful, as I say, for setting up old bits of gear, particularly old scopes, which it's I've used it a number of times for. So that works, still works well, and we can just demonstrate the deviation control. Hopefully, if we just get those a bit further apart, just wind the deviation control, and you can see that works nicely too. Let's have a look at the high frequency outputs. We'll probably have to turn the volts per division up. Let's reset our trigger level. Where are we? I'm not sure get any output at all from that. It probably is, but it's probably too fast for the scope, to be honest with you. And I'm not terminated. I'm sure this output does work. There is something clearly there, but it's not very clear. I just check I haven't got bandwidth limiting on. No, we haven't. So it's no, it's not very clear actually, and I think it's. What's that? Is that just noise? Yeah, I think I'll have to check that on another scope, on a faster scope, but I'm pretty sure that still works. I must admit I haven't checked it recently. It could be faulty, that. The trigger output connection here. Let's get our levels back. Let's go AC coupled. Okay, so there's our trigger level output. So there are fixed frequencies, precision frequencies. Let's just check those marker output again with AC coupling, because it might have been. No, I can't see anything on the. Possibly because I'm not terminated correctly, but I can't see anything on the outputs of those. It might be something there, but it's all a bit noisy here. There may be something here underneath all this hash. Let's measure this with the cursors. Let's see what we've got. We've got one there, and we've got one. So we've got 10 megahertz output, and it's 100 nanoseconds, which is this is supposed to be 5 nanoseconds. So maybe that stage isn't working. I can have a look at that at a later stage. So we could check our output levels with a DC voltmeter. So let's get a meter and sort that out. Okay, hopefully you can see that. So let's check our DC level. So we'll set it to 0.1 volt and the multiplier on 1. So I'd expect to see 0.1 volt on the output here. I'm only using just the leads across the B and C. We should have 0.1 volt there, and you can see 0.099. So we can turn it to the 300 millivolt range. 99.9. So that's good. The deviation's turned off. This should be 200 millivolts. This should be 300 millivolts. Oh, sorry, 500 millivolts. You can see that's good. It's amazing, these meters. Wherever you turn them, there seems to be reflection. There's 500 millivolts. 1 volt. 2 volts. Let's go times 2. 4, 3.99. Let's go times 4, 8 volts. So you see it's actually also a pretty good calibrator for setting references and checking even meters and things like that. It seems to be extremely stable. I'm not sure about these high frequency outputs. I can look at that maybe that'll be another repair video. But yeah, I just thought I'd show you the workings of this, and if anyone's interested, or maybe try and investigate why the outputs, these high frequency outputs, are not displaying anything. It does actually. I just noticed there it says deviation off, so maybe it will only work when I have the deviation off, which I didn't have. Let's have a look. Oh, looks like I've got an output. There we go. Okay, so the scope's now showing. Let's turn around properly. An output. So let me just. This is the 5 nanosecond output. Let's just check it, see what it says. We'll do it manual cursor mode. And sure enough, that's 5 nanoseconds. It's a bit difficult to measure it exactly because it's a sinusoidal waveform. We've got 2 nanoseconds here, but you have to adjust the trigger. Or walks with division. Come on. Where are you? Yeah. We're running into sort of. You see the way the scope builds up slowly because it's running in alternative time. It's not running. It's it's doing like the Tektronix do, where they build up the waveform. It's not in real time anymore. We're probably looking. This ringing here is down to poor coupling, or because I haven't got termination on the scope. Let's get that to try and trigger it better. Let's try and measure these between these points here. This probably won't be the right point. So that's showing 10 nanoseconds, but we're looking for 2 nanoseconds. So 2 nanoseconds is probably that peak there. But it's making out, but I haven't terminated it properly, as I say. And the lead I'm using is a resistive lead as well, so that's not great. But you can see the scopes showing some output, and I'm pretty confident when I checked it on another scope a while ago, it was working fine. So yeah, thanks for watching, and more to come. Well, after I finished the video, I thought I'll pop the top open and have a look inside, and it always had a bit of a funny smell to it. It's just an old bit of test equipment. They all have their individual smells. I was looking to see if there's where the connections went to these high frequency outputs, because even though there was output, one of the outputs was very erratic. And I've just pulled out one of these capacitors. I did recap the main power supply board down here a couple of years ago, but I've just come across these 2 capacitors here. These are the 4700 microfarad at 16 volt, and Elco caps. Good quality make of capacitor, made in Germany. Date code, not too sure. It's certainly not 41. But look what's happened. Can you see what's happened to the end of the can? It's leaking out electrolyte all over the place. So it's going to need a recap, even if I don't use it. This is pretty revolting. I'm just going to put it across the capacitance tester, and it's measuring. Once it's set, well, it says 7 millifarad, 7,000 microfarad. Well, that's clearly not right. So it's possibly leaky. Do a resistance check, ESR check, and it shows an ESR of 0.036. But the trouble is, we know this capacitor is obviously failing, and it's probably leaky. So often you need to do a resistance check just to see if it draws any excessive current. And what I tend to do is either use a low voltage thing, cap like this, just apply voltage across it to see if it draws any current. So we're going to wind it up to its 416 volts, and it's drawing current. Not a lot, but clearly this capacitor has seen better days, and this is going to be replaced. So I need to replace 2 electrolytic capacitors that are on the main board here. You can see this is on the main board. There's the other one there, and the one I've just taken was from the top there. You can see. So replace those 2 capacitors because there was about 600 millivolts of ripple on current on that. So these caps are obviously not doing what they should do. So let's see if I can find some capacitors. Okay, I found a couple of capacitors. Tossing, I don't know what these are like. They're probably a load of rubbish, but this says they're made in Japan. I don't know if they're Chinese copies. I've got them in my junk box. Now they're 4,700 microfarad, but they're 25 volts. So in theory they should last longer. They're only 85 degrees. I'm just going to check them on the capacitance meter just to see what they measure. When it finally works out its range, I put it actually on capacitance will help. And we have come up with 4,400 microfarads, 4,400 that one measures, as opposed to the one we've just taken out that measures when it finally finds 6,800, which that's a classic sign actually. If you check a capacitor and it's reading a lot higher than it should do, it possibly means the capacitor's actually is leaky. And that's actually one where like the things like the old solar American high voltage capacitor test is quite good, because you can apply voltage and see if it's leaky. So yeah, they both check good. They've got a low dissipation factor. So I'm going to replace these two capacitors now. And that's the smell. I've got it looks like Marmite on your hand. I don't know what the electrolyte is. It's probably carcinogenic. I'll probably be dead in a couple of years. But certainly you don't want to really get it on your hands. And if you do, you want to wash your hands immediately afterwards, which of course I will do anyway. I always do when I touch any of this equipment in here. This old gear, any gear actually, anything that's sort of got any flux or any electrolyte on it. Always wash my hands afterwards. So let's get these two capacitors out. Let's check this one as well. This one's leaked as well, but not quite as badly. I don't know if you can see that. So let's check that on the capacitance meter. Now I know a lot of people will recap these devices without, just as a matter of course. Yes, I think it's probably a good idea most of the time. Yes, he's measuring a similar sort of thing, 6,800 microfarad, but it's clearly its days are numbered. So yeah, I mean, if you went through the whole thing, and you could replace all the electrolytics. There's a couple of these Philips blue capacitors in here. I don't know if you can see them. There's typical stuff you find in Philips gear. They're not bad as long as they're in a cool operating condition. I tend to find they fail in power supplies and things like that. So what I'm going to do now is just desolder those holes. Clean these holes out with a soldering solder sucker. So let's do that now. You can use solder braid, or you can use one of these old solder pumps, or you can buy a proper desoldering station, which I should do really. I'd like to get one. I've been spoiled a bit by the ones we have at work, and I know all the gear No Idea uses paste equipment, very nice, good quality stuff. All this is old hand-me-down stuff. This is an old OK soldering iron that we used to use these at work, but got rid of them because they're so hard to keep the temperature in calibration. Perfectly good enough for my workshop, and because it doesn't get an awful lot of use, it's lasted well. But as for desoldering gear, this is really all I use is solder braid and this solder pump, which seems to work fine for me. So the holes are clear. Let's unplug that. It leaves a bit short. Let's get the capacitors in, making sure you put them around the right way, of course. Not a huge amount of room to work in here. It's probably that this piece of equipment's been left on in the calibration department when they're calibrating, and it's sort of like been on day after day, year after year sort of thing, and that's why these capacitors have failed. Because really, when I spoke to people, they said they hardly anyone ever remembers using it. So I think, as with all electronic gear, I suppose you are supposed to plug it in and leave it on, though that's sort of changed in the saving the planet, sort of everyone's telling you to turn the stuff off now, so people are coming around and turning the gear off in the workshop when you're just about to take a measurement. I mean, in theory, a lot of this equipment should be well and truly warmed up before you actually use it. Certainly meters and oscilloscopes and things like that should really be left on for at least an hour, so their references are all set and stable and things like that. So let's get the second capacitor in. Let's try and what I'm going to do is just bend a little and just show you. So you can see the wires are here, to this top wire here, just out of frame. I'm just going to bend that slightly just so it holds it in position. This is a ground connection, as is this one. Okay. So wire cutters. So it's important to make sure that if the capacitor's been kicking around for a while, it's fairly clean. I've just given these leads a scrape with the pliers just to get any oxidization off. And I'll just snip that wire off. Seems okay. Good. Sorry, I know you can't see at the moment. Let's do this bottom one now. That solders to this outer braid of this screen lead here. Nice connection, good. Okay, just check to make sure we haven't got any solder bridges or anything horrible like that. And you can see our two capacitors in the circuit now. Just straighten them out to make sure they're not touching anything and they look nicely aligned. That's it. Just make sure that the two inner leads don't touch. Don't think it matters, but the leads are common. It's hard to see actually. So that's good. Those two capacitors are replaced. So I think whilst we're on a roll of capacitor changing, and I often get criticised for not changing enough capacitors by my followers. They seem to think that everything should have its cap being replaced as soon as you plug it in. We need to just see if there's any other capacitors here that need to be changed. Now I think I've changed a couple of these capacitors down on the other boards underneath the transformer. Just have a look to see. There's a couple of caps here that actually you might replace. I need to see them behind that transformer. Come on. Got two capacitors here, there and there. I want to replace those two as well. I'll certainly get them out and measure them, but I would have thought if I get them out I might as well change them anyway. So let's pop those out. So it looks like these two leads here. No, I'm soldering the right thing. It's always a bit tricky to trying to work out what to unsolder when you're working on the side of the board. Where are you, little buggers? Okay, I'll pause the video and once I've got the capacitors out I'll continue. Okay, these are the capacitors taken out. They're Elners, and they 100 microfarad at 6.3 volts. I've put them on the checker. They've got very low ESR, and they read about 110 microfarad. So they are absolutely fine, and they're going to go back in. They're not. The reason why these sort of capacitors probably haven't failed is because they didn't handle the high ripple current from the power supply. Those two caps I've just replaced are basically the smoothening of the rectifier, so they've got a lot of ripple current and they're going to wear out quicker. These are post-regulation and don't have a lot of stress. They're just basically decoupling capacitors, so let's get those back in. I've just pulled out the front panel meter after replacing that little capacitor, and I see there's another one of those caps in here that I'm going to pull out and replace as well. We've also got a linear regulator here, looks like the 5-volt regulator, and also this capacitor here, 1000 mic, so that needs replacing as well, or certainly taking it out and checking. And we've got another smaller Phillips capacitor down here that I'm going to also look at. So let's get that capacitor out and get that on the checker. Okay, got this on the tester, and it looks like it's pretty handling the 5 volts. This one hasn't leaked, as you can see. It's quite clean here. It's measuring at 6,000 UF, and its dissipation factor is 0.17, which is pretty good. But I think I'm going to try and find something to put in there. I don't know if I've got anything of that value, but as the other ones have failed, I think these are probably well past their sell-by date anyway. So let's see if we can find another capacitor that will replace that one. Okay, I couldn't find a radial, but I found an axial. I found a radial. 16 microfarad at 4,700. It's checking 4,200, 4,300, and dissipation factor is good. So we'll pop that one in if it will fit. Now the only thing is the spread of the board may be a bit tight. I'm not sure we're going to get that in. In the meantime, if I can't find anything, I don't think that's going to fit actually. I'm going to have to spread the legs particularly high, and it can't sit off the board because the meter gets in the way. So I think what I'm going to have to probably do is put this one back in for the time being, the original one, and see if we can find a better capacitor. Well, it looks like luck's on our side today. I found a last one, another one of these toss-in 4,700. So brilliant. Let's put one of these. Let's put this in, and then we'll check the other capacitors down at the bottom here. These other Philips ones, because they usually dry up. Those they don't usually go leaky. They just dry up. So let's get this back in. It's always a good idea to check to make sure you get the component in the right way, and I think that is the wrong way. Yep, capacitor's around the wrong way. That wouldn't be good. What it would probably do is it would go into a current limit on the power supply, will probably blow the fuse actually. A big capacitor like this around the wrong way will usually put up quite a bit of resistance before it explodes. So let's get that there. Always double check your capacitors. When I capped the Rodin shorts a couple of years ago, it's amazing, I went through and checked it all, and it all looked fine, and then I thought it wasn't performing properly. It was sort of, power supply seemed to be loaded down all the time, and I went back again, double checked, and I'd missed one of the capacitors. One of the capacitors under a heatsink was round the wrong way. Changed that round, and that fixed that problem. So it's always worth double checking, and it's also worth actually photographing when you're doing stuff like this. I'm not photographing now because obviously the video camera's running, so I've got a reference to if anything is wrong. So that's that one. So that's the 3 big electrolytics in there. Let's get this Philips 1000 mic out and see what this one measures like. So this is 1000 at 25. So let's plug this into the LCR, see what we get on this. And I'm doing all this at 120 Hertz, so it's a bit slow to range. And it's measuring exactly 1067 with a 0.095 ESR, so dissipation factor. So it looks like, let's see what it is, and 110 milliohms ESR. So I think that's good. That capacitor is fine. I don't think I'll have anything to replace it with anyway, so let's pop him back in. I don't think that's going to cause a problem. we got that little one at the top there, just below the big capacitor I've just replaced. Probably won't even bother checking that one, to be honest with you, because it's more than likely to be fine. As I say, that's not going to have any sort of ripple current through it or anything. Good job to get these caps back in position. Okay, so those caps are back in. So that's the main part of the power supply, the main filtering, the unregulated supply repaired. Let's pop the thing back together and then let's see what it does. Okay, the unit's back together again, and there's no obvious change in its performance. Obviously it's probably drawing less power from the mains because the caps aren't leaky. We've probably got better filtering. Now the problem is with this high frequency output, I've terminated it now so you can see on the scope what it's doing. And if you can see here, it's basically going nuts. It's like modulated with a low frequency or like almost like a sweep generator. If I stop it, you can see we've got this sort of like this frequency, and it becomes corrupted then starts again. So there's clearly something wrong with that part of the circuit. And that will probably mean a bit of investigation to work out what that is, and maybe that's something for another day. I don't know if that's going to be of any interest to people. It's probably to do with one of these timing boards down the back here. A number of timing boards that these high frequency outputs run from, and you've got these boards here. And this is the master oscillator one. I've sort of put my hand around it to see if I could get it to affect anything, but clearly there's something seriously wrong and unstable there. At first I thought maybe that's a power supply problem, but I don't think it is. I think what we will do though is we'll get the scope on the all the rails just to check their ripple and check their voltages, make sure they're okay. Especially as we change the capacitors, it might be worth just verifying that the rails are as they're meant to be. So maybe that's the next thing I'll do, is I'll check the voltage on the capacitors and the test points to see how they fare. It's funny how you think you know what you're doing sometimes. I've been looking at this power supply that I recapped. I thought those heat sinks, I wonder if they're getting hot. And I've just touched them, and I tend to touch things like that without sort of making sure I've got a no ground return, and just got quite a shock off it. So you know, I was thinking these are probably low voltage regulators, and they're probably switching sort of 300 or 400 volts, and it's probably the high voltage part for the DC output, the 200, 300 volt supply. So there's a word of warning to everyone, and most people know this, and you don't go poking around. There are certain parts of the circuit you know are safe, you know, all the logic boards you can poke around with, all this sort of side is fine. You have got high voltage here, you know that this is a main supply incoming. Usually anything after the transformer is safe, but of course it doesn't mean it's not stepped up for a high voltage output like it was there, and you get a bloody wallop of it. It wasn't a nasty shock, it wasn't a dangerous shock, but it's one that, you know, one of those typical ones that, and it was AC. You could feel the buzz of it, so it was like it felt like a square wave sort of feel to it. It had a real bit of a kick to it, but so you had to be pretty careful. So yeah, the next thing to do is I'll have to dig out the manual wherever I put it, and then we'll see if we can work out if there's a procedure for checking and calibrating these HF outputs. Okay, interestingly enough, with this isolated scope, this Fluke 199C, you can see here that the frequency is actually 5 microseconds, and we haven't got that effect we got on the Hewlett-Packard scope. Now that's caused, I think, by, and I've seen this with other problems, is because the scope's connected to an isolation transformer. There's like an eddy current or some sort of circulating currents that cause a problem with sort of certain measurements. I think if I took the scope off an isolation transformer and plugged it into the same supply that the Ballantine is using, this is the result you'd get. And you see here that output's working, and it's accurate. It seems to be triggering fairly well on the scope. So It doesn't look like it's a problem there. The 2 nanosecond output, however, doesn't seem to have any output at all, or if it has, it's very, very low. You can see here it's a bit jittery, but it clearly is working. Let's try and get a better resolution. Remember how to work this triggering on this thing. This is a nice scope actually. It's a pity its channel 1's doesn't work because one of the ASICs has blown up and you cannot get the replacement ASIC. That's all it is. It needs another ASIC. Channel A just doesn't do anything. Channel 2 is fine. Now I don't know how we adjust our trigger levels. Trigger level on manual. So do you adjust it here? Yes, here's our trigger T here. So you can see there we have, it looks like it's still 5 nanoseconds and we're connected to the 2 nanosecond output terminal, so I don't think that's working correctly. That's the fastest the time-based scope will go, but no, you can see that we're actually still at 5 nanoseconds. That 2 nanosecond output connection doesn't seem to do anything. You see there, you can see it's the same frequency. That's the 5 nanosecond and that's the 2, no change in frequency. So that needs looking at, and that might be just an adjustment, so we can possibly have a look at that next. Okay, that 2 nanosecond output connection goes back to this little SMA or little plug-in connector. I don't know what they call these. Someone will tell me. So that's our connection to the 2 nanosecond output, and it goes to this capacitor here, which is like a trimming capacitor. We've got various traps and things on this board, so it could be something as simple as this board's out of calibration. So I think I'll end this video here, and then we'll maybe the next step is I'll just try and perform a calibration on this unit and see if we can get this output working correctly, and just check it's only this side of the unit I'm interested in calibrating. We know the DC level's good, but it'd be nice to get that output working. Anyway, thanks for watching, and second part to come. Okay, for those of you who are a bit more on the ball than I am, and that's probably the entire population, we're not ever going to see anything on the scope at 2 nanoseconds, because that's 500 megahertz. The other output we confirmed with the fluke meter was working fine, and that's just connected this up now actually to the Rakel counter, and we're on the 5 nanosecond output, and you see here the Rakels showing you. Let's choose period. So if I go back to the other channel and select period for A, we adjust the level correctly. Where are we? Termination. Oh, come on. Period. I had this working a minute ago. Bear in mind this isn't a particularly clean output. We're looking for sort of 5 nanoseconds. There we go, and sine waves, so 5 nanoseconds. So despite the waveform being pretty noisy, you can see that that's 5 nanoseconds. And if we select over to the 2 nanosecond port, we've got to switch channels, unfortunately, because it will only, this channel A will only go up to 160 megs. So we've got to select frequency B, because it hasn't got period, and then you see 499.99 megahertz, which equates to 2 nanoseconds on the output. So that shows that this actually is working correctly. I just didn't know what I was doing. No change there. So the recap, I've done a recap on it. It looks like it's working really well. I've got rid of that horrible smell that actually the unit generated because of those leaky capacitors, and I'll show you a bit of a close-up. This is the meter, deviation meter here on the front panel. These are all parts of this. Is the deviation control. That's the power supply with the capacitors we replaced. The other capacitors down underneath the meter here. This is the DC selection. There's the heatsink that gave me a wallop. There's some caps in there I've replaced at previous times. And you can see it's all sort of typical of its era. That sort of style of layout, plug-in boards. This is the 8 high frequency side. This is the time-based side. This is the part that does all the. This is the main oscillator board here, and you see that little gold connector in the middle of the picture there. That runs out to this connection here. So yeah, nice little bit of kit. Quite rare actually. I've only seen a couple of these on eBay. Ballantine stuff is always was regarded as pretty good quality. You know, it's not in the same league as Hewlett Packard and Tektronix and stuff of the same time, but it's certainly not poor quality, and it's nicely made. But it's still got that slightly, dare I say, sort of British build quality to it. Slightly sort of almost like it's a kit, but clearly stood the test of time. This unit and is working really well. Anyway, thanks for watching, and more to come.